Okay, so we're now on to our final part, which is Newton 3. And what Newton 3 is I just mentioned it earlier, each action has an equal and opposite reaction. This basically means that if we have a body A exerts a force on a body B, the body B will exert an equal force in the opposite direction, and this is true whether the bodies are stationary or accelerating towards each other. So I'm going to jump straight into an example, and this is a classical example for this sort of thing. So the question says, a light inextensible string passes over a fixed smooth pulley and carries particles of mass 5 kilograms and 7 kilograms, each at one end. If the system is freely moving, find in terms of G, we want to find the acceleration, we want to find the tension in the string, and we want to find the total weight exerted by the pulley, so total force. So we'll put a sigma there. So, okay, so let's draw a picture out of how this looks. So if this is our pulley, we have a string that goes over the top. We have two weights. One is 5G and the next one is 7G. And we know that this is going to be accelerating something like this here, and it's going to be accelerating something like this here. So we're going to need to use force equals mass times acceleration at some point, okay? So, but we don't have a force. But what we do know is there's a tension force here and there's a tensile force here. This is why we call it an inelastic string. We're keeping the same tension force. If you were to pull from one side to the other side, the force stays constant throughout the string. So now we can begin to resolve this. So if we start with this being particle A, we'll call it, and we'll call this particle B. To resolve our particle A as this is moving upwards because this is the lightest. So first of all, we want to say force equals mass times acceleration. So if we, is this not going to work? So force equals mass times acceleration. So let's work out our upward force. So first of all, we have a tension force, which is that one, which is T, and we're going to call that positive. So what do we have going down? Well, we have our minus our 5G, and then we can say that that is equal to our mass times acceleration. Force equals mass times acceleration. Likewise, if we solve B now and we solve downwards, we could say, well, 7G this time is going to be, well, our tension force this time is going a different direction, is going to be negative, so that's negative T plus, so we're going in the different direction, so positive 7G equals 7A. So all we need to do then is we can just simplify this into a pair of simultaneous equations. We can say that is the same as saying T minus 5G equals 5A and 7G minus T equals 7A. If we were to add those together, we have a nice set of simultaneous equations. This would disappear, and we would say that 12G equals, so our 12, no, we wouldn't, we would have negative 5 plus 7, so we would have 2G equals 12A, therefore A would equal to 1 over 6G. Okay, so that's quite simple, that our acceleration would be equal to A 1 over 6G, and of course this would be in meters per second squared. Okay, so the next part of the question asks us to work out what the tension in the string is. Well, again, that's quite straightforward because as we can see here, we've actually got a set of simultaneous equations. So we can just choose one of these simultaneous equations, and if I can get this to move, we can say that we know this here. So T minus 5G equals 5A. We've just worked out what A is. So T minus 5G equals 5 over 6G. And if we were to just neaten that up, we would find that T therefore would equal, T would equal, just a bit neater, we stick it into the calculator, we would find that would be 35 over 6G. So we've just used the simultaneous equations to work out G for our second point. Okay, so, and then finally, it asks for the total force which is acting upon the pulley. Well, we can think of this, we actually have two T's here, so actually the total force is going to be equal to 2 times by T. So we could probably just say quite simply that we know what T is, that's 35 divided by 6, so the total force equals 35 divided by 6G times by 2, which equals 35 divided by 3g. Okay, so that would be our total force, and that would be full marks in the exam. Okay, so I'll do a slightly more difficult example now. Actually, I think this is one of the most difficult examples we do in the whole course. So again, this is question B in the book. It says two particles of masses 1 kilogram and 3 kilograms are placed over a pulley on a light inextensible string. So so can't write that there. So that's 1 kilogram and this is 3 kilogram. And they're placed 2 meters above the ground. So this is our ground. And they're both held at rest and they're going to be released. So when they're released, we're going to have an acceleration, which is going to be coming up and down here, A. And what we're asked to find out is what is the total height that the second particle, this particle on this side, will reach. So we know what's going to happen is as this hits the ground, it doesn't bounce, as it says in the questions, it'll come down and hit. But this second particle will have an acceleration. It still has this acceleration, so it's going to keep on traveling. So we get asked to find the total height in which it reaches. So as previous, we know that our tensile forces are the same in the string because it's inextensible and it's inelastic. So what we can say here is, right, okay, so the first thing we're going to do is we're going to do what we've done previous, and we're going to try and calculate what our acceleration is. So first of all, we're going to say, well, it's pretty much the same as what we did before. So our first tension force up from if we side this side A would be T minus 1g equals 1a mass times acceleration, and we have 3g minus t equals 3a. Okay, so we have this set of simultaneous equations. If we add these together again, we'll find that 2g equals 4a, so a equals 1 over 4g. Okay, oh sorry, 1 over 2g, a half g, or g over 2. Okay, so that's okay. We know this acceleration. We know what this is accelerating at. So we're now asked to find the maximum height which this will go to. So what we need to know is we know we can use our Suvat equation. So we're going to say our initial velocity was at 0. We don't know our final velocity. I don't know if we need to know our final velocity. We don't know our time, but we do know our acceleration. Okay. So we might need to work a few things out. So for the motion of the 3 kilograms, it has to travel 2 meters here. So maybe we need to work out the time it takes for this to travel here. Was it say for the motion of 3 kilograms over the distance of 2 meters? Well, we know that this is u here. On this side, u equals 0. We know that a equals half g, and we know that s equals 2. Okay, so we know that side. So we could calculate the final velocity perhaps, and what would that give us? Okay, so that would give us the velocity in which the string becomes slack. So that's going to give us a certain time. Okay, so our final velocity would be, we'd have to use the equations of motion v squared equals u squared plus 2as. That one would do. So v squared equals 0 squared plus 2 times a half g times by s, which is 2. So we can find that our v squared is equal to, v is equal to the square root of 2g. Okay. So we can fill this in here as the square root of 2g. So we have a little bit more information. Right, okay. So what else do we need to know? As there's no longer any more tensions, so they're going to keep on moving upwards. So that was the final velocity. So this would then become maybe the initial velocity. So it's reached its maximum height, it's traveled that distance, and then we have an initial velocity where it's then going to reach a final velocity of 0. So let's think about this now. So we realized that this was accelerating. The maximum velocity we could accelerate to was this, and that's where it lands at rest. So we have that this has moved 2 meters. This the particles dropped by 2 millimeters, 2 meters, sorry, and then it's given this particle 1g, this a velocity. So now its initial velocity is going to equal the velocity which it ends at here, which is 2g, square root of 2g. We know that the final velocity it's going to equal is 0. And what else do we know? We know its acceleration, because we've finished as it's speeding through. We know its acceleration is just going to be negative g, which is gravity. And I think that's all that we need, because all we want to calculate is the distance. So again, we can use v squared equals u squared plus 2as. So we can say that 0 equals 2g plus 2 times a times by 2 times g times by s. So if we stick this in, we find that s equals 1 meter. Okay, so as this ball's dropped, it's finally hit the point here. This has had an acceleration, or it had a velocity, initial velocity. So this velocity has then kept it going, but then the acceleration has been pulling it back down to Earth, which was gravity. So what we can see is, well, we've worked out the height in which it's jumped. So we know that's 1 meter, but that's not correct, because we've got two other things to work out. Is actually this particle has moved down 2 meters, and this particle therefore would have moved up another 2 meters. So that would be 4 meters if we add those two together. So that would mean that our total distance would be equal to our 1 meter that it's kept on going in the air, plus our 4 meters. So our s, the amount it's the highest point which this particle go to, is 5 meters. And that would be the answer to the final question. That is tricky. That's a really tricky one. I'm not sure if we'll have anything that comes up in the exam like that. We'll have to see. But anyway, that's been the mathematics course, and that's been Mechanics 2. I hope you've enjoyed it. Apologies for any typos you might have seen in the book. And in the final lecture, we'll be going through revision, but this is the final YouTube video.